Okay, so here we are, 2.1. So mathematical systems, direct proofs, and counterexamples. So a mathematical system consists of axioms, right, and definitions and undefined terms. And what we're going to talk about here in this section is how to prove things within such a mathematical system. There's many different examples of, Euclidean geometry furnishes an example of a mathematical system. And so you have these axioms like, given two distinct points, there is exactly one line that contains them, right? In Euclidean geometry, given a line and a point not on the line, there is exactly one line parallel to the line through the point, et cetera, et cetera. And there's many other structures within mathematics which constitute a collection of objects along with axioms and about those objects and the relationships that they have to each other. Okay, so we're going to talk about, first thing we're going to talk about is called a direct proof, right? So here's the idea. They look like this typically. Theorems are often of the form for all x1 through xn, right? So you're talking about for all these objects, if p of x, x1 through xn, then q of x1 through xn, right? So it's provided, this is true, provided that the conditional proposition p of x1 through xn, then q of x1 through x1 is true for all x1 through xn, et cetera, et cetera. So here's the idea. So a direct proof, right? A direct proof assumes that we have p of x1 through xn is true, and then using that as well as other axioms and definitions previously derived, right? Theorems and rules of inference, we want to show that q of x1 through xn is true. Okay, so let's take a look at this. Let's look at this example. Okay, so here's a definition. Really, it said if n is even, we say an integer n is even if there exists an integer k such that n is equal to 2 times k. That's the definition of even number, even integer. And an integer n is odd if there exists a k such that n is 2k plus 1, definition of odd. So let's see what this is. This one example is to give a direct proof of the following statement. We would like to prove that for all integers m and n, if m is odd and n is even, then m plus n is odd. Okay, so you think about that, and you have there's this idea that we have this. The idea is the hypothesis is that we're going to assume, right? That's the thing that we assume is true, that m is an odd and n is an even, and we'd like to conclude that m plus n is odd. Okay, so here's their talk about what to think about, but you ask yourself, based upon the hypothesis here, so if m and n are even, well, what does that mean? Well, it means that there's this k1 and k2 such that, first off, m has to be equal to 2 times k1 plus 1, and n has to be equal to n times k2 plus 2 because it's even. So you use the definitions, and what you're trying to do then is to exhibit the conclusion. Okay, so then in this discussion they talk about how you can't make any assumptions on k1 and k2. They're just two integers, right? Okay, so basically let's look at the exact proof. They're just talking about the thing here. So you do exactly that. You say let m and n be two arbitrary integers, right? And suppose that m is odd and n is even. Well, we will prove that what we want to prove here is that m plus n is odd. So now we're going to use our definitions. So by the definition, since m is odd, there exists an integer k1 such that m is equal to 2 times k1 plus 1. Also, by the definition, since n is even, there exists an integer k2 such that n is equal to 2 times k2. Now let's just add them together. Now the sum is, you just add them together, and then you use the distributive law, which is the fact that we can factor the k out, and we see that m plus n is equal to 2 times k1 plus k2 plus 1. Well, that means, right, that means that m plus n is an odd integer because it's of the right form. Okay, so that's the idea of a direct proof, and there are other examples in your textbook that you can read through and check out, and there they are. But I just want to do one example for you. Let's see. Okay, here's the idea. We also need to know how to disprove, right, a universally quantifying statement. So suppose somebody came up to you in the street and said, well, here, they said, the statement for all n in the positive integers n 2 to the n plus 1 is prime. Suppose they said that that's true. Well, you'd have to come up with what's called a counterexample. And so to show that the statement for every n in z plus 2 to the n plus 1 is prime is false, you just need to come up with one counterexample. So notice if we take n is equal to 3, then since 2 cubed plus 1 is 9, and that's not prime, that is enough to prove the statement, prove that the statement is false. Okay? All right, so that's in a nutshell what's going on in 2.1, and there are some problems that you should do for homework, and yeah, it should make some sense. Okay, all right. Thank you very much. Bye bye. Hope that helps.